Hello everyone. Myself Nupur Mittal. I am faculty from Ajay Kumar Garg Engineering College, and today I am going to deliver the lecture on the topic signal flow graph. Previously, in the last lecture, I have discussed in the previous lecture, I have talked about block diagram representation system. So I have discussed there that it was difficult to, if a given system is complicated, so it is very difficult to analyze the system as a whole. So block diagram representation is one of the method that came into picture so that we can conveniently solve the complex network. We can conveniently analyze the complex network as a whole by connecting different blocks in series or by connecting different blocks, right? Now, if a system again is a complicated system, then SFG is another method, especially when a set of equations are given to us, then we can use this SFG method. It is a better method as compared to block diagram reduction method because when a system is very complicated, so in case of block diagram representation, we have to draw the block diagram after every single step, right? But in case of SFG, once the system is defined, once the set of equation is given to us, we can easily find out the transfer function of that particular system. So it is another method of representing a complicated network in a convenient. So these are the basic contents of today's lecture. First, I have already introduced about give the introduction about the SFG. In the next slide, I will discuss more about SFG. What is the definition of SFG? See, signal flow graph can be written in short as SFG. Okay. So in the next slide, I will discuss what is SFG and what is the definition of SFG. What are the basic elements being used in SFG? Okay, and what is the advantage of SFG over block diagram method? And then we'll discuss some terminologies that are being used to define the SFG. Then what are the properties of SFG? We'll talk about them. Then how to construct SFG from any given complicated network. We'll discuss about that. Then we'll discuss the method how to convert block diagram into SFG. Then the formula which is known as Masson gain formula, it is used to describe the SFG. We'll discuss about this, and at last we'll discuss some example based upon this Masson gain formula. Okay, so now as I have already told you that SFG is a further simplification of block diagram, right? Here in case of SFG, the blocks, in case of block diagram, we have used the blocks, the summing point, the takeoff point. These all are replaced by the two elements, that is the node and the branches in case of SFG, right? So we can define SFG as the graphical representation of the variables of a set of linear algebraic equation which are representing a particular system, right? So these two basic elements are node and the branches, right? Here these nodes are represented by small circles and all the dependent and independent variable are represented by these nodes. And the line joining these nodes, the line connecting these nodes is called a branch, right? This branch is associated with arrow, with the signal, which is with a signal which is carrying the information, right? So a node is assigned to each variable of the system. A separate node is actually assigned to each variable of the system, and branches are basically used to relate those nodes. These branches are used to connect one node to another node. These are basically defining the mathematical relationship between the two nodes, right? Let us take an example, a very simple example of Ohm's law, which is described by the equation V is equals to IR. This is nothing but the Ohm's law. Here we have two variables, voltage V and current I. So voltage V and the current I are representing the two nodes, and these are connected by a branch which is having a gain represented by R resistance. So you can see here that the voltage V, this variable V, is dependent upon the current I, another variable called I. And these are connected with each other through this transmittance, or you can say gain, called R. Right? So here you can see that we can easily write V voltages is equals to I into R. So it is defining that voltage V is dependent upon the current I, and it is when a signal, see, when a signal from any node is coming to another node, it get multiplied by its gain. Okay, so signal I would get multiplied with R and it will become V is equals to IR. Okay. So the main advantage of SFG is that it is a straightforward procedure, and it is available for finding the transfer function. It is a very straightforward procedure for finding the transfer function of any complicated network. While in case of block diagram reduction method technique, it is quite difficult as well as time consuming. Why? Because in every step we have to make the block diagram again and again. Okay. Sorry. Now the terminologies that are being used in defining the signal flow graph. So I have already told you, first one is the node, right? So the node is represented by small circles, okay, small circles, and these are used to basically show the variables of the system. Each node, separate node is assigned to a separate variable, individual variable, right? You can consider this figure. Here they are we are having 4 nodes, Y1, Y2, Y3 and Y4. Okay, that means the 4 variables Y1, Y2, Y3 are associated with the 4 nodes. Okay, now there are basically 3 types of node in a system. One is the input node, or you can say source node, right? Another one is the output node or the sink node, and third one is the mixed node, or you can say it as a chain node. This is one. Okay. So what is input node? The node which is having only outgoing branches is called the input node. The node which is having branches with only outgoing signal, right? That is called as the input node. So in this figure you can say Y1 is the input node here. It is having only outgoing branches, okay? The signals which are leaving a particular node, okay, that is called a input node or the source node. While the output node is having only incoming branches. It is not having any outgoing branches. That means the node which contain only entering signal, that is known as the output node or the sink node. Here you can say Y4 is the output node. And the node which is having both incoming signals as well as the outgoing signals. That means both the branches are in the node at which both the branches are entering as well as branches are leaving. That is called as the mixed node or the chain node. That is, here you can see Y2 and Y3 are the mixed node. Here at Y2, this branch is entering and this branch is leaving. Similarly, at Y3 you can see this branch having a transmittance of B is entering and a branch having a gain C is leaving. So here Y2, Y3 are the mixed node, Y1 is the input node or the source node, and Y4 is the output node or the sink node. Okay, mixed node I have already told that it is having both entering as well as the leaving signals. Okay. So here again, this is another example. You can see here X1 is the input node, right? X8 is the output node here, and these X2, X3, X4, X5, X6 and X7, all these are the mixed node. X2, 3, 4, 5, 6, 7 are the mixed node. Okay. Now what is branch? I have already discussed that the lines which are joining one node to another node in the signal flow graph is basically known as the branch. This branch is actually showing the relationship between the two nodes. Branch is basically associated with the arrowhead as well as with the transfer function. We know that the transfer function is the mathematical approach. Okay, and the arrowhead represents the flow of the signal from one node to another node. And this mathematical operation, this basically branch shows the relationship of one signal. Branch shows the relationship of one signal on another to produce the output, right? Now coming to the forward path. Forward path is basically a path which is proceeding from input towards the output, right? You can see here in this figure, this is the forward path, X1 to X2. There are many forward paths. So here we can see in this figure the forward path which is started from the input towards the output. That is known as the forward path, right? So X1 to X3, X1, X2, X3, X4, then 5 till 6, 7 and till X8. This is one of the forward path, right? Another forward path can be formed here. You can say this can also be represented as the forward path. Okay, it must be from X1 to X8. Okay, there could be a number of forward paths in a particular signal. So SFG is not just like block diagram is a unilateral property of the system. This SFG is not the unilateral property of the system. By writing a number of equations, we can form different SFG of a particular system. Now what is feedback loop? The basically loop, it is a loop which is started at a particular node, right? Which is started at a particular node and ending to the same node, but at least travel through one node, okay? And without tracing any node twice is known as the feedback loop. So a loop which is formed through a path which is starting from a particular node, right? Starting from a particular node and end at that particular node, right? Traveling at least one node without tracing any node twice is called a feedback loop. So here you can see this is the feedback loop that I have formed. This will be the feedback loop. It is started from here, node number 1, let's say 1, 2, 3, these are the 3 nodes. It is started from node 1, it is traveling another node 2 and then till another node 3 and then it is ending at the node 1 only, okay? And there must be no repetition of the nodes. No node should be traced twice in case of feedback loop. So here in this figure you can see we are having 2 feedback loops. One is started from X3 to X4 and coming back to X3. Another one is X2, then X3, traveling to X3, then X4, 5, 6 and going back to X2. So these are the 2 different feedback loops in this particular figure, right? And I will tell you the gain in the next slide, okay? Now another one is the self loop, right? Self loop is the loop which is having only a single node, right? It is started at a particular node and then stop at that particular node. It does not involve the second node. The self loop is having a single node It is start from that node and end to that node, and it does not travel to another node. While in case of feedback loop, the loop must travel at least one node. Okay. So here in this case, you can say X5 is a self loop. The loop formed by the node X5, which is having a gain F, is called as the self loop, right? So path in such loops are never defined by a forward path or any feedback loop, right? As they never trace any other node of the graph. Now, what is path gain, right? What is path gain and what is the loop gain? So when a signal flows from in a forward path, right, then the product of gain of each branch gives the overall path gain. So here you can see, if we talk about a path gain from node X6 to X8, then the path gain will be from X6 to X7, the path gain is I, and from X7 to X8, the path gain is J. So from node X6 to X8, the path gain will be I into J. The product of the paths, the product of the gain of both the path will be the path gain of the particular system. So here, if we talk from start from node X1 and end at node X8, then the path gain from X1 to X8 will be A into B into C into E into G into I into J. So this will be the path gain from node X1 to X8. Right? This is the forward path gain. Now, if we talk about the loop gain, so loop gain will be the gain formed by the particular loop. Okay. So the product of individual gains of the branches that are in the form of loops is said to be the overall loop gain. Okay. So here you can see, if we talk about the loop, feedback loop X3 to X4, then back to X3, then the loop gain will be the product of the gains of these two branches, that is from X3, that is from X3 to X4, the gain is C, and then from X4 to X3, the gain is D, right? And the loop gain will be the product of these two gains, that is C into D will be the loop gain. Okay. Now, what are non-touching loops, right? When two or more loops do not share a common node, that means when two or more, there could be two non-touching loops, there could be three non-touching loops. Let's talk about the two non-touching loop, right? In case of two non-touching loops, there must not be any common node in between the two loops, right? See, here in this figure, this X3 to X4 till X3, the two nodes are involved, X3 and X4, right? This is one of the loop from X3 to X4, right? And another loop could be X5 only. It is at node 5, right? So you can see in these two loops, there is no node common. Two non-touching loops means the two loops do not share a common node. Then such loops are called as the two non-touching loops. If we talk about three non-touching loops, then the three loops do not share a common node, right? Then they will be the three non-touching loops. So here in this case, we have these two non-touching loops, X3 to X4, then back to X3 and X5. These are the two non-touching loops. Okay. Now the properties of the signal flow graph. So the first property of the signal flow graph is that the signal will flow from one node to another node through the branch, right, and in the direction of the arrow, right. This particular signal flow graph, it is applicable only to linear time invariant system. The linear systems and the systems which are not varying with the time, and the system which are not varying with the time, as well as the system which obeys the Ohm's law, is this system is applicable for the SFG. SFG is not applicable to nonlinear system. It is not applicable to time variant system. Okay. Now, the third point is that the signal flowing through a branch gets multiplied by the gain, or you can say transmittance of that particular branch. And this product will be equivalent to a node where that branch is terminating. Let's take an example. We are having this two nodes, okay. Let's say this is x2 and this is x1 and it is having a gain 4 here. Okay? So, here x2 will be equal to, there is a relationship between x1 and x2, and x2 here will be equal to 4 times of x1. So, signal at this node, that is x1, will get multiplied with the gain, branch gain, when it is traveling through it to produce the another variable x2. Okay. Another property of SFG is that the value of the variable will be the algebraic sum of the signals coming to a particular node. Let's say we have a node x2 and the three variables are entering to this node. This is x1, this is one node which is say x1, another node this is x3 and this is x4. Okay, let's given the gain, see this is 2, let's say this is -3 and say this is 4. Okay, so x2 will be the sum. There will be a relationship between x1 and x2, there will be a relationship between x3 and x2 and a relationship between x2 and x4. So, x2 is dependent upon these variables x1, x3 and x4, and the exact relationship between these variables will get when these variables will be multiplied by their branch transmittance, by their gains. So, here x2 will be the algebraic sum of the variables which are coming towards it. Okay. So, we can write x2 as, here we can write x2 as equals to 2 times of x1. In the previous property, I have told you that the signal get multiplied with the gain. Okay. So, this will be, this branch is entering, another branch is entering from x3. So, it will be 4 times of x4 and this will be -3 times of x3. So, this will be the relationship between x2 and x1, x4 and x3. This x2 is dependent upon the variable x1, x3, x4 here. But these variables x1, x3 and x4 are independent of the variable x2. They do not depend upon x2. Okay. Another point is the value that a node represents is not affected by the number of outgoing branches. As I have told you, x1 is not dependent upon x2. Okay. It is depending, x2 is actually dependent upon x1. This is the property, what I am trying to say, that the node is not affected by the number of outgoing branches. Let's take another example. See, if we have a variable here at the node and we have, say, these 5 variables, these 5 nodes. See, let's say this is x3 and this is x1, incoming signal is 2, and this is x2 and it is -3. Okay, and these are outgoing signals from x3. This is x4, x5 and x6. It is having a gain 1, it is having 4 and it is again having a 3. So, here x3 will be equals to the 2 times of x1 and -3 times of x2. It is depending upon only the incoming branches. Its value is depending upon the variables, those are incoming towards it, right? It does not, this x3 does not depend upon the variable x4, x5 and x3, while x4 is dependent upon x3, while x5 is dependent upon x3 and x6 is also dependent upon x3. So, from here we can write x3 is equals to, from here we can write x3 is equals to 2 times of x1 minus 3 times of x2, right? Yes. So x3 is dependent upon only these two variables. So we can write the equation of x3 only on these two variables. Only these two branches are incoming towards x3. While the 3 branches which are going away from x3 can be written as x4 will be equals to 1 times of x3. It is a separate equation between x3 and x4. x5 can be written as 4 times of x3, right? And similarly, x3 can be written as, similarly, this x6 will be equal to 3 times of x3. Hope my point is clear to you. So the next point is, the signal flow graph is not a unilateral property of the system. It's not a unique property of a system, because by writing the equation in different manner, we can draw a number of SFG of a particular system. So it is not a unique property, while the block diagram is an unilateral property of a particular system. Now, how to construct the SFG? There are basically two methods to draw SFG. First one is by using the system equations, and the another one is by using the block diagram method. Okay, so first one, let's discuss these two methods one by one. So the first one is when we have the system equations with us, then while we drawing the SFG from the system equation, these steps must be kept in mind so as to draw the SFG. The first method point is, first of all, represent each variable of a system by the individual node. Okay. Then second one is, as the value of the variable at a node is obtained by summing up all the signals that are coming to that particular node, then draw the branches accordingly to that particular node. And the third one is, the coefficient of the variables present in the equation will be the gain of the branches that are joining the nodes. And the last one is, locate the input and output variables of the equation separately to draw the signal flow graph. So this is the example. See, this is the example we are having. We have to construct a SFG from these equations. So one of the equation given to us is y2 is equals to a12 into y1 and a42 into y4. That means y2 is having the two nodes that are incoming towards it. First one is having a variable y1 and again a12. Another one is having a variable y4 with again a42. Similarly, y3 is dependent upon the two variables y2 and y5, right? And y2 is y2 is the node which is coming towards the y3 node with again a23, and y5 is a node, is a signal which is coming to another node y3 with again a53. Similarly for all, right? Now let's make the signals, these nodes, one by one. So first of all, here you can see, let's say a y6 is the output, okay, and because it is not depending on no other node is dependent upon y6, and y1, let's say it's the input, okay. So here we can draw as y1 and y2, 3, 4, 5 are the variables, okay. y1 is the input node, y6 is the output node, and y2, 3, 4, 5 are the variables here. So let's draw first one by one. Let's say this is a y2, right? Okay, and a node y1 is connected to it, and the gain is a12 here. Okay, another variable, let's say this is y3, this is y3. Say this is y2. Now this is, let's say this is y3, another node. say y4, this is y5, and let's say this is y6. Okay, now it is easy to draw. Okay, now at y2 we have a12 and another node is coming from another branch is coming to y1 from y4, that is with a gain a42. We can draw it like this and we can write the gain of this loop. Now y3 will be equals to y23 into y2 and ay53 into y5. So from y2 we can draw this like this, and this will be a23. Now y5 is connected to y3 with the gain a23. y5 is connected to y3 with the gain a23. ठीक है. Now y4 is connected to y3 with the gain a34. And y5 is connected to y4 with the gain a45. Right, and y5 is also equals to a35 into y3. That means a35 into y. Now y6 is equals to a56 into. So this is the required SFG. So you can see that I have drawn like this only. So here I am representing single diagram for each equation, and then when we combine all these diagrams, we'll get this particular SFG. So there is no need to draw a single diagram for a single equation. You can draw directly SFG from all these equations. Okay, first carefully analyze the equations and then draw the SFG. So this will be the overall SFG that I have formed in the previous slide. So here you can see that y1 is the input node, y6 is the output node here, and y2, y3, y4 and y5 are the 4 variables. Okay, and this is the forward path from y1 to y2 towards y3, then y4, y5 and y6 is forming a single forward path. Another forward path is formed by y1, y2, y3, then y5 and y6. So there are basically 2 forward paths, okay, for this SFG, and we are having 2 feedback loops here. One is from y2 to y3, y4 and then back to y2. Another one is y3, y4, then y5 back to y3. So here you can see there is no non-touching loop, as these 2 loops have a common node y3 as a common node. Sorry, y3 as a common node. So there is no non-touching loop in this, and there is no self loop in this SFG. Okay, there are 2 forward paths. Okay, and the gain of this loop y2, y3, y4 will back to y2 will be a23 into a34 into a42. Similarly, gain for this forward path will be the multiplication of all these gains a12 into a23 into a34 into a45 into a56. Okay, I hope the SFG funda is clear to you when a set of equations is given to us. Now let us discuss the another method, how to draw the SFG when a block diagram is given to us. So these are the steps that have to be followed when a particular block diagram is given to us and we have to draw the SFG. So first step is represent all the variables, all the summing points and all the takeoff point of the block diagram by nodes, right? Represent eliminate all these variables, summing point and the takeoff points by the nodes to draw the SFG, right? Then second point is represent the blocks of the block diagram as branches in the signal flow graph. Like connect these nodes with the branches. Okay. Third one is represents the transfer function inside the block of the block diagram as gain of the branches in the signal flow graph. As we have done in the previous slide also, the gain of the branch is same as the transfer function of the block in case of block diagram representation. Okay. Then last one is connect all these nodes as per the block diagram, and if there is a connection between two nodes, right, then represent the gain of that branch as one gain. As in block diagram representation, as we have shown that if there are two nodes, two blocks are connected in series, we can represent them with a single block by simply multiplying their transfer function. So here in SFG also, we can represent the connection between the two nodes, right, with the single gain, and that gain will be the multiplication of the two gains. Okay. For example, between summing points, between summing point and a takeoff point, between two summing points, or between a summing point and a takeoff point, or between input and a summing point, and between a takeoff point and a output, right? Now see this example. This is the block diagram which is given to us, and we have to draw the SFG for this particular block diagram. You can see here, we can, what I have told you is represent each and every summing point, each and every takeoff point as a separate node, right? So here we can represent the 9 nodes, take this RS as a separate node. So here you can draw this RS either with a separate node. Let's say this will be X1, let's say this is RS, a separate node. Then for this summing point, another node Y1, this Y2, then there will be a summing node between G1 and G2. Then there could be a node for this takeoff point as Y4, we can name it. We can name this summing point as Y5. We can name this summing takeoff point as Y6 as another node. Then this summing point is represented another node as Y7. This takeoff point, another node, can be represented by Y8, and this takeoff point as another node Y9, right? Now connect these nodes, right? And since we have a block in between Y2 and Y3, right? So we can represent it like this. This is Y2, this is Y3, okay? We can represent it. See, G1 is the transfer function of this block. So we can represent it by the G1 as the gain of this branch between the nodes Y2 and Y3. Similarly, G2 is the transfer function between the two nodes Y3 and Y4. So you can write it at Y3 and Y4, and you can represent it as G2. Okay. Now you can see similarly the Y4 and Y2. We have a feedback loop here with the gain H1 and a minus sign. So you can draw it like Y4 and Y2. You can connect it like this. The signal is like this, and the gain will be minus H1. We have to consider these signs of the summation point. Okay. Similarly, you can draw this. Then we have this. See, let me clear it. We have this RS. Okay. Then Y2. Okay, sorry. RS is coming to this Y1. Another node Y1. Y1 is a node, and the gain between RS and Y1 is 1, and the gain between Y1 and Y2 is also 1 here. Okay. Now coming to Y4 and Y5, the gain is again 1. Then from Y5 to Y6 again gain is 1. Y6 and Y7 gain is G3. From Y7 to Y8 gain is again 1, and between Y8 to Y9 gain is G5. Now we can see that gain between Y8 and Y1 is plus H2. We can draw a feedback between Y1 and Y8. It is a feedback which is having a gain of plus H2. Similarly, you can connect all these. Between Y6 and Y7, we are having a gain of G4. Okay. So you can connect it like this. This will be the graph of the previous block diagram. So you can see here I have shown the gains with the signs. So we can draw the SFG in a very simple manner from the block diagram. So that's all for today's lecture. I will discuss the Masson gain formula in the next lecture. Thanks a lot.